Okay, so let me bring this back a little bit. So I want to show you what happens when you have some water and you put it over a candle. So you can see down here, there is some soot, but it comes off. The plastic is not being burned. So you can put it on here for quite some time and you're not going to have any burning of the plastic. All the energy is going into warming the water up. Now, the water has a high heat capacity. It can absorb a lot of energy before changing its temperature. And because it's a very high heat capacity, you're not going to see the plastic melt for a very long time. Until the water gets a high temperature, the plastic stays very cool. So just to prove that, here's an empty bottle. Do the same thing. You see that? I don't know if you can or not, but you can see that the bottle's melting pretty fast. So the water kept the bottle cool. Now it's sizzling. But plastic has a very low heat capacity. It heats up incredibly fast with a low amount of energy. And so while the water protected the plastic, on its own, the plastic heats up very fast because it doesn't hold very much heat before changing its temperature.
So Miss Polly?
Yes.
So basically, if you had another liquid in the water bottle, like the same plastic water bottle that had a higher heat capacity, it would melt faster?
That's a good question. Yeah, definitely it would.
Okay.
Yeah, so now the thing is that pretty much everything that we drink is water-based. We really don't drink anything that's not water-based.
Yeah, true.
But yes, if you had something that was not water-based, then that would be true. But even alcohol, most of it is water that we drink. Even with an alcoholic drink, it's maybe beer is like 5% alcohol. So even beer, it's 95% water. Now other things are higher or lower, but alcohol itself also has a high heat capacity. It's about half of water's, but it still is pretty high. So alcohol too can absorb energy pretty well, but not quite as well as water can. That's a really good question. Let me go ahead and change this back to the whiteboard. We'll go from there. Okay. Just one thing to go over today, and then we'll do a few homework questions. So if something feels hot to you, heat is being emitted from the object to your hand. So if something feels hot, it's hotter than you are. You're feeling the energy go from that object to yourself. Heat flows from object to you if it feels hot. And vice versa, if something feels cold, then heat leaves your hand and goes to the object. So that explains why, if you go from walking on, say, tile floor to carpet, the tile feels cold to you, even though it's the same temperature as the carpet. So if you're in one room, it's the same temperature. But if you walk from tile to carpet and back to tile again, the tile feels a lot colder to you than the carpet does. And that's because energy is leaving your feet and going into the tile. Tile is able to absorb energy from your body better than carpet is. And because of that, you think tile is colder than carpet, but it's only based on energy leaving your body that you think it's colder. It's the same exact temperature if it's in the same room. Now, notice both times I said heat is moving. So if something feels cold to you, we don't say that cold goes to you. We're saying that heat leaves you. Because cold doesn't exist. Cold is the absence of heat, but cold itself is not a thing. I'm going to write that down on here. So cold is just the absence of heat. Heat is a real thing. Heat is energy that's being transferred. But cold is just the absence of that heat. It's like you have a hole in the wall. You know, that hole itself is not really anything. The hole only exists because you have a wall around it. Take away the wall, you don't have that hole anymore. So the hole is just the absence of the wall. The hole is just where the wall is not. So the hole itself is not anything. It's just because you have the wall around that you have the hole. Cold is the same, you can think of it the same way. Light and dark also, you can think of it the same way. Dark is the absence of light. Dark is not a real thing either. So light is real, light is energy, but dark is just the absence of light. So if we say how dark something is, all we're saying is how much light is not there. And then, you know, think about philosophy too, good and evil. Evil is just the absence of good. So you only have evil based on how little good there is present. So it's the same thing as you think about light and dark or hot and cold. Evil is just the absence of good. Evil is where there is not good. So you can also argue that evil doesn't really exist for the same reason, because evil is the absence of good, cold is the absence of heat, dark is the absence of light. They all follow the same idea. Okay, on page 321, let's go through example problem 2. So page 321, they're showing you a calorimeter. And so it's that silver tank. And it says that it contains 0.5 kilograms of water. So the mass is 0.5 kilograms. And the water temperature initially is at 15 degrees Celsius. And then you put a 0.4 kilogram block of zinc. And its temperature originally is at 115 degrees Celsius. And you place that zinc into the water. They're asking, what is the final temperature of the system? So over time, this zinc is going to give energy off to the water. The zinc is at 115 degrees Celsius. The water is at 15 degrees Celsius. So heat will leave the zinc and go into the water. So by losing heat, the zinc will cool down. The water will heat up until they're at equilibrium, where the same temperature with the zinc in the water. So the final temperature will be the same for both. So the T final temperature of the water will equal the final temperature of the zinc. So T final of water will equal T final of zinc. Because they're in the same environment, they'll transfer energy until they're the same temperature. So based on that, we can solve this problem. The energy that leaves the zinc will equal energy that enters the water. Q of water, Q stands for energy, will equal negative Q of zinc. Whatever energy zinc lost, the water will gain. So we'll use that equation. And so we know that Q equals MCAT. So we'll use the MCAT equation for both sides. And just plug in the values that we have. Okay, so on this side, mass of the water, it's 0.50 kilograms. Next is C of water. If you look on page 318, you can find it. It's 4,180. So put that in for C of water. Delta T We don't know the final temperature, but initial temperature is 15 degrees. And then for the zinc, it's going to be negative Q of zinc, mass of zinc, 0.04 kilograms. C of zinc, you go to page 318 and look it up, it's 388. Running out of room here. It's down here. Then right here, what you should have would be T final, which again, we don't know, minus T initial, which is 115 degrees Celsius. Now, even though the units for C are in Kelvin, we can keep it in Celsius. So we don't need to convert that to Kelvin. We can keep these in Celsius. They'll cancel out. Okay, so all I need to do now is just multiply what we can in solving this problem. So we'll multiply 0.5 times 4180 to start with, and then distribute that to both of these terms, and then go from there. Does anybody have that 0.5 times 4180?
I think it's 2,240.
Okay.
Yeah.
And then notice right here, the kilograms will cancel out there. So now our units are joules over Kelvin, and then T final minus 15 degrees Celsius.
Wait, it's not 2,240.
Oh,
It's 2,090.
2090. Close. All right, 2090. Okay, and then on the left-hand side, I'll go ahead and multiply this out. So 0.04 times 388. What do we get for that? Anybody have that?
I mean, I probably did it wrong again, but I got 15.52.
Okay, that sounds right.
Wait, so it was 0.040 times 388?
Yes.
Okay,
You
yeah.
got 15 point what?
15.52.
Okay. Okay, cancel out kilograms again, so we get joules over Kelvin on that side as well. And then in that parentheses, it should be T final minus 115 degrees Celsius. Okay, so now we can distribute on the left-hand side 2090 to both sides. So 2090 times T final minus, and then do 2090 times 15. Does anybody have that?
I have 31,350.
Okay, 31,350. Okay, and then notice right here, we'll just cancel out the Kelvin and the Celsius. Those will cancel out. We have joules for the unit right there. Then on the right-hand side, same thing, distribute 15.2 to both sides. So we get 15.52 times T final. And then negative 15.52 times negative 115.
I think negative 1,784.8, but could be wrong.
That sounds right. And then be careful with this because we have a negative right here and a negative right there. So this will become a positive now. And we get 17.84. Cancel out the Kelvin and the Celsius. So that unit is in joules now. So now what we can do is isolate TF. Doesn't matter what side, but if this is a negative right here, we'll just go ahead and put that on the left-hand side. So we're going to add 15.52 times TF to both sides of the equation. And then we're going to add 31,350 to both sides. Okay, so for the first one, we do 2090 plus 15.52, 2,105. So following the sig fig rules, we don't need to include the ones place on here. So we'll just keep off this right here because the last sig fig was in the tens place right here. And so we would not only we couldn't add to the ones or beyond it. So we'd have to report to this place value right here. So well, we might as well just change it to that then. So because we can't report it below the ones place, our answer would be 20, 1, and then 10. We have to round it up to the tens place. And that's times T final. And then adding 31,350 to both sides, we do 17.84 plus that. And we get 33,134 joules. Divide both sides by 2110. And we get T final. We need 2 sig figs. So the answer should be 16 degrees Celsius. So the water did not warm up very much. Even though the zinc was at 115 degrees Celsius, the water only changed 1 degree Celsius at the end. It can absorb a lot of energy before warming up. Any questions about that before we go on? Okay, on page 319, today do question, actually, sorry, not page 319. Page 321. Do question 7 on that page, and then go on to the next page and do 12 through 18. I'll go ahead and clear this and put this on here. So question 7 on page 321. And then on the next page, do questions 12 through 18. When I put in grade length, there's going to be a quiz tomorrow. It'll be over what we learned this week in class. Just to give you more warning, because I don't know if I told you yesterday about it, I'll have the quiz on Thursday instead, just to give you one more day, but it'll be over what we learned today and Monday. So I'll say quiz on Thursday, over Monday and Tuesday. And just like I did before, it'll be over homework questions that I had you do. So really just today, because we didn't have anything yesterday, did we? No, we did. So yesterday and today's homework could be on the quiz on Thursday.
Miss Holly, will it be like one math question and like 3 vocab like the last one?
Yeah, most likely it will. Yeah, I think so. So yeah, study your notes from Monday and Tuesday, and study your homework questions. And yeah, it'll be very similar to what you had for the last quiz, where yeah, about 3 vocabulary questions from your notes on Monday and Tuesday, and then 1 homework question that you did either today or yesterday.
Okay.